Hi, I'm going to talk about double integrals over rectangles. This is section 15.1 in the Stewart textbook. I'm not going to cover every detail of the section. There are links to additional resources, including extensive videos from other channels. And there are links to that in our course Blackboard site. So I invite you to take a look at that. What I'm going to do is I'm going to assume that you've already seen those other videos and you know the basic ideas, and I'm just going to add a few details. To start with, though, I'm going to do something a little bit easier. To start with, we're just going to see some figures. Some figures that correspond to how integral is assigned volume. So in this figure, we have a graph of a function, z equals f of x, y, and the function might go on more widely, but we are restricting to just a rectangular domain in the xy plane, and we're only looking above that rectangular domain. And if we integrate f of x, y over this rectangular domain, the integral would be the signed volume between the xy plane and that graph. Signed volume means that when the graph is above the xy plane, we get the volume, the positive volume. And if the graph is below the xy plane, like in this figure, then the parts that are below contribute negatively to the volume. So we would take the volume above the xy plane minus the volume below the xy plane. This is reminiscent of single variable calculus, where the integral is the area between the curve and the x-axis, but really it's not the area between them, it's the signed area between them. So the area above the x-axis counts positively and the area below counts negatively. Well, it's the same thing here with signed volume. In this figure, by the way, the domain is again a rectangle. See the four sides here. And we can look at domains that aren't rectangles. Like in this figure, we could have a domain that's a funny shape. So there's a graph of a function, but if we were integrating over this funny shaped domain, we would just take the volume contained in the sort of funny shaped cylinder. It, I guess, has vertical sides and a flat lower surface, but the upper surface is curved, following the graph of this function f. So that's the signed volume interpretation of integrals. As we go forward, we'll see other interpretations, other meanings and applications of integrals, but the signed volume is a good place to start. Some things to notice about these integrals. For one thing, you have to specify what domain you want to integrate over. That's normal. In single variable calculus, we have to specify the a and b to say integral from a to b. What's maybe a little different here is that the shapes can be so strange, right? We could have rectangles, we could have these lumpy shapes. That didn't happen in single variable calculus. They were just intervals, and an interval can't have that many different shapes, right? It's just an interval. These can have a real wide range of shapes. So that's something that we're going to have to talk about as we go forward. In this section, we're going to concentrate on the case of rectangles. So it's a little bit simpler. And we'll postpone dealing with these kinds of domains, but just be aware that the domain is something that has to be specified. Okay, now having said that, I have a question for you about these domains. So the question for you is, in this integral that you see here, what is the domain for this integral? Is it a square, the disk, the whole xy plane, or a sphere? You can pause the video and think about it if you like. The answer is a disk. The answer is a disk. You see the domain labeled here at the bottom of the double integral sign. And this, if it was x squared plus y squared equals 1, that would be a circle. To put less or equal 1 is filling in that disk. That's a disk domain. Next question, what does the graph of this function look like? The function that's being integrated, the function inside the integral. So in other words, this function, the square root. What does that graph look like? A plane, a sphere, an upper hemisphere, a lower hemisphere, a circle? What do you think? Pause the video and think about it. The answer is an upper hemisphere. If we solved for z, if we squared to get rid of that square root, we would have z squared equals 1 minus x squared 1 minus y squared. And if we added the x squared and y squared onto the other side, we would have x squared plus y squared plus z squared equals 1. The equation of a sphere. So this corresponds to a sphere, but z is just the positive square root. It's only the upper hemisphere. Now, the third and final question in this chain, what is the value of this integral? We haven't learned any rules for finding integrals like this. So you could pause the video and think, how can we find this? The answer, first of all, the answer is that the volume is 2 pi over 3. How did we find that? We used the signed volume. Remember, this graph is the upper hemisphere of a sphere of radius 1. And so we're looking for the volume between the xy plane and that hemisphere. That would be 1/2 of the volume of a sphere. And the volume of a sphere is 4/3 pi r cubed. It has radius 1. If you write out the volume of the sphere and then half of that to just be a hemisphere, you would get 2 pi over 3. All right, now to start to see how these integrals work, let's talk about Riemann sums. This topic of Riemann sums, I want to add a little bit of context. It's foundational for how integrals are defined. If you care about theory, then Riemann sums is part of the story of the theory of integrals. If you just care about computing integrals, Riemann sums play a kind of limited role in terms of computing integrals. There's something to that story, but no, if somebody says find this integral, you're not going to typically write down a Riemann sum to try to figure it out. It comes back when we talk about applications and interpretations. Like, what does this integral represent? Maybe it represents the total mass of an object or the total electrical charge in a region or something. So later on, when we talk about that, the Riemann sums will be kind of central to that part of the story. So the context is that Riemann sums are not necessarily central for purposes of computing integrals. We're going to see how to use our usual fundamental theorem of calculus, antiderivative stuff. And we'll see how to do that soon. But to help set things up, let's start with Riemann sums. So in this slide, I have a whole bunch of figures. Let's say we have a rectangular domain, and notice this notation. This product notation means we're taking x, y pairs where the x can be from a to b, the interval a to b. So x can be in the interval from a to b, and y can be in the interval from C to D. This is pretty common notation for rectangles, this kind of product notation with two intervals. They're just giving you the x interval and the y interval that way. And this is showing the resulting x, y's that have the right values of x and y. To do a Riemann sum for an integral here, we would divide this rectangle up into a bunch of little rectangles. And then from each little rectangle, we would choose a sample point. Commonly, you would say take the lower right corner of each rectangle, or the upper left corner, or whatever, or the center of each rectangle. In this figure, they've drawn it with choosing apparently a random point in each rectangle. But one way or another, you choose a sample point in each rectangle. Next thing we do is we look at the function value over that sample point. And you imagine a pillar of that height that starts at the xy plane and goes up to the graph of the function. And if the graph of the function is tilted or curved, then you specifically pick that sample point as the height. Now we have a pillar whose volume is, it's a big box, right? The volume is the length, or I guess it would be the length times the width times the height. So the delta x times delta y times the height, which is f of point P. And that's the volume of that box. In the last part of this drawing, they've drawn all the boxes. It's a little hard to see every single one of them, but you can sort of see how all the boxes are there. And the Riemann sum is to add up the volumes of all those boxes. As you can see, that would be an approximation to the volume under that graph, between the xy plane and the graph. It's not exact because the actual region has a smooth curved top, and all these box pillars have sort of, it's kind of a stair-step jagged surface on top, but it's an approximation. And if you've taken calculus before, you can guess how we're going to get a better approximation. Just subdivide more finely, right? Subdivide into smaller grid. And if you subdivide it smaller and smaller and smaller and take the limit, then you're taking a limit of Riemann sums. And as long as that limit converges, that's the integral. The Riemann, so to reiterate, in this part of the drawing here, you see the volume of one box is delta x times delta y times the height, f of a point. In the limit, that delta x, delta y sort of becomes a sort of quote-unquote infinitesimal dx dy for the area of the base, and then you multiply by the height, f of the point, f value for the function f. So that's a picture of Riemann sums, and hopefully it helps explain why the Riemann sums correspond to that volume, which is the integral, and taking the limit of Riemann sums would make it give you the integral in the limit. Now, of course, in theory, you could write down a list of these points and the list of function values and then just add up all the numbers. Well, probably you would have a computer do that rather than do that by hand. And this is a way that computers can numerically evaluate integrals, is by using Riemann sums like this. So this is one of the ways that numerical integration is done, is with Riemann sums like this. But when we're computing integrals in class, we won't really do that. That's kind of a different situation that we won't get into. Last observation here, if you were going to add up all these columns or all these pillars, how would you do it? Would you just sort of add them up in random order? You'd probably be organized about it, right? And you'd go across the rows, you'd add up the first row, and then add up the second row, and then add up the third row, and so on like that. Add up each row, and then record the row totals, and then add up the row totals. Or you could add up each column. You could add up the first column, and add up the second column, and add up the third column, and add up all the columns and record the column totals. And then add up all those column totals to get the total. And it would be the same thing, right? These pillars, they are what they are, and we're going to total them. So it's the same thing if we put all the row totals and then add up the row totals, versus if we put all the column totals and then add up all the column totals. And what are those row totals and column totals? Well, the row totals, if you add up across a row, if you add up across one of these rows, that would be a Riemann sum of an integral where y is a constant and x is a variable going from a to b. So the row totals would just be integrals where x goes from a to b and y is a constant. And then we're taking all the row totals from y equals c up to y equals d. And that brings us to Fubini's theorem. The integral that we're looking for with all those pillars, we get the same thing. If we integrated from x equals a to b, that would be one single row, and we're treating y as a constant in that inner integral. The inside integral here is treating y as a constant, and x is going from a to b, and then we take all the rows. We start with row y equals c, and we go up to row, the last row where y equals d, and we add up all those row totals. That would give us the integral, and it would be the same thing in this integral here. First we're doing the columns. We're taking the column from y equals c to d, and then we're adding up all the columns. And our first column is when x equals a, and our last column is when x equals b. We're just adding up all the columns, or each column is given by the integral with respect to y. That's kind of, and so I hope that makes sense and adds some context to the videos that you watched or the textbook section that you read. In a way, that's kind of the main thing I wanted to add. They're very nice videos from other creators. I just thought they could have explained this a little more in a little more detail. There you have it. I have a few closing thoughts, but that there was the main thing I wanted to get across. I hope that made sense. A practice question. Here you see an iterated integral. When you write a dx, dy, or dy, dx, and you have integrals with separate bounds written there, that's called an iterated integral. What's the domain? The answer is, oh, it didn't show it. The answer is A. The answer is A. X goes from 4 to 9, and Y goes from 3 to 6. So the answer is A. Now, if you watched the Calculus Blue videos with Professor Greist from the University of Pennsylvania, you saw that one of the things he emphasized is that usually, typically, um, integrating is not the hard part in these problems. The hard part is setting up the integral and getting these bounds of integration right, uh, the limits of integration. I couldn't agree more. It's really challenging. Students struggle with this, so pay attention to how we set up the integrals and pay attention to these domains. So imagine that these integrals are nested one inside the other, and the inner integral has 4 to 9 dx. That's how I know that x is going from 4 to 9. The outer integral has 3 to 6 dy. That's how we know that y is going from 3 to 6. Here's an example. So it's an iterated integral. Do you know what's the domain? This time the inside integral has integral from 0 to 5 dy, so y is going from 0 to 5. And the outside integral has 0 to 4 and dx, so x is going from 0 to 4. The function that we're integrating is x plus y, 1 over the square root of x plus y, which is to say x plus y to the minus half power. We can use the power rule to integrate it. So add 1 to the power, we get x plus y to the positive 1/2. And we have to divide by that power. We have to divide by half, which is the same thing as multiplying by 2. That's an antiderivative, 2 times x plus y to the 1/2. And we were integrating for y from 0 to 5. Plugging in y equals 5 and y equals 0, we get 2 root x plus 5 minus 2 root x. And that's an integral dx. Now it's just an ordinary integral from calculus 1. This is x plus 5 to the 1/2, and an antiderivative, we could use the power rule. We could add 1 to the power, make it x plus 5 to the 3/2, and then divide by 3/2, which is the same as multiplying with 2/3. And same thing here, x to the 1/2, the antiderivative is 2/3 x to the 3/2. And we already had a factor of 2 from before, so we get 4/3 instead of 2/3. And then we just plug in some numbers, x equals 4, x equals 0, and there's some arithmetic, 9 to the 3/2. Would you do 9 cubed and then take square root of that? Or would you take 9 and do the square root first and then cube that? I think the second one is easier, right? You don't have a big number along the way. You can have a small number and cube it. If you work out the arithmetic to the end, this is the value of the integral. Finally, the last thought is about separable functions. A separable function is a function f of xy that can be separated into a product, a function of x times a function of y, like g of x times h of y. And there's a cool simplification. If you have a separable function, and if your domain is a rectangle, which in this slide it's drawn as what's written here is an integral whose domain is a rectangle, then there's a cool simplification. F of xy is g of x times h of y, and for emphasis and clarity, we've drawn parentheses around that inner integral. They're always there, but a lot of times they're kind of implicit. But in this step, we drew them for clarity to highlight what's going to happen next. So what I want to highlight is that in that integral, that's an integral with respect to y. It's got a dy here. That means that we're treating x as a constant. And that means that g of x is just some constant value. It's just some scalar multiple in this integral. And you know, one of the properties of integrals is if you have a constant scalar multiple, you can pull that out in front of your integral. And that's what we've done here. We've pulled that g of x out. It's a constant scalar multiple. It gets pulled out in front. Next, we have an integral with a dx. That means that x is a variable, and this inside parentheses is a constant. In fact, it's literally a number. It does. There was an h of y, but it got integrated, and you get a number. It's constant. This inside parentheses doesn't have any x's in it. So that means that it's a constant multiple, and it can be pulled out of the integral. This time we've pulled it out to the right instead of to the left. So we pulled out this constant multiple integral of h of y, and this is the result that we wanted to get to. I've walked you through step by step and the justifications for each step, but the conclusion that I wanted to reach was that if our function is separable, it's a g of x times h of y, and if our domain is a rectangle, then this integral can be written as just the integral of the x part times the integral of the y part. It's a nice shortcut. So if you see a separable function on a rectangular domain, it can save you a lot of work to do the integral this way. Okay, that's it. Thanks for watching. Bye.